will induce an EMF in the ring. Now you notice that if the current flows in the clockwise direction, if the current grows in the clockwise direction in this coil, the induced current will be in the opposite direction. In other words, Lenz's law says the direction of the induced current will be such as to oppose the very cause of it. You must understand that statement very well. Alright, let's do another example. A uniform magnetic field makes an angle of 30 degrees with the axis of a circular coil of 300 turns and radius 4 centimeters. The field changes at the rate of 85 Tesla per second. The field changes at this rate, means the rate of change of flux is given there. Find the magnitude of the induced EMF in the coil. All these are simple, straightforward problems. Well, what are the things we know? We know that the number of turns is 300 turns. We need the area of the coil. We are given the radius, so use the radius to find the area of the coil. And we are also given the rate of change of flux, dB by, well, we are not given the rate of change of flux. Go and watch there. You are given the rate of change of the field. So dB by dt is given. Now there is a difference between the rate of change of field and the rate of change of flux. So always distinguish between the two. The flux linked with the coil placed in a uniform field phi b is NBA cos theta. So here, distinction between flux and the field. So what you have been given is the rate of change of field. We can use that to find the rate of change of flux. So the induced EMF E is given by, what's the induced EMF is? The magnitude. The direction we can leave it aside. The magnitude of the induced EMF is the rate of change of flux, d phi by dt, which is d by dt of this quantity, NBA cos theta. Well, here N, A and theta are constant. They are changing. But what is changing? Only the magnetic field is changing. Therefore, E equal to d phi by dt, d by dt of this quantity, we can take out Na cos theta. So E equal to Na cos theta times dB by dt, and we know all those values. So substitute all the known values, and that gives you the induced EMF is 111 volts. Another one. An 80-turn coil has a radius of 5 centimeters and a resistance of 30 ohm. At what rate must a perpendicular magnetic field change to produce an induced current of 4 ampere in the coil? So here you are given the induced current. You need to find the rate at which the magnetic field changes. What is dB by dt? So we got n equal to 80 turns. The radius is given, therefore we can find the area of cross-section, pi r squared. And the current is known and the resistance is known. Well, first we find the induced EMF by using the resistance and the current values. Well, we are given the induced current, we know the resistance. If you know those two, we can calculate the induced EMF. What is the induced EMF? We have a induced EMF E is I times R, and that will be 4 ampere times 50 ohms, that is 200 volts. And this 200 volts must be equal to d phi by dt. The induced EMF is a measure of the rate of change of flux. Well, since the magnetic field is at right angles to the plane of the coil, theta equal to 0, and therefore cos theta is 1. So we have d phi by dt. Phi therefore is NBA, and d phi by dt will be d by dt of NBA. And here n is a constant, the number of turns of the coil. A, the area, is a constant, and only B is changing. Therefore, write it as NA dB by dt. And this NA dB by dt equal to E, and you know that E is 200 volts. Therefore, we say dB by dt, therefore, equal to E divided by NA. That is 200 volts divided by 80 turns times 0.00785 meters squared, and that is 318 Tesla per second is the rate at which the magnetic field is changing. So always distinguish between the rate of change of field and the rate of change of flux. Another example. A rectangular coil of 80 turns, 20 centimeter wide and 30 centimeter long. You can see the length and width gives you the area. Is located in a magnetic field of 0.8 torr directed into the plane of the paper with only half the plane of the coil inside the magnetic field. Well, if you say the magnetic field goes into the board, the coil is situated like this. That's the coil, the rectangular coil, and the field is into the board, and the coil is going to be moving in and out of that field. Alright, the resistance of the coil is 30 ohm. Find the magnitude and direction of the induced current if the coil is moved with a speed of 2 meters per second to the right, 2 up, and 3 down. Well, watch this diagram. Here, that indicates a magnetic field that is into the board. You can see we use X's to show the field is going into the board, and we will use dots to show the field is out of the board. So this is a magnetic field that is going into the board, and here is the rectangular coil of 80 turns, 20 centimeter wide and 30 centimeter long. Now, with only half the plane of the coil inside the magnetic field. In fact, I have put more than half inside the magnetic field. The whole of the coil is not in the magnetic field, only half of it. So this is 20 centimeter, this is 30 centimeter. If E is the induced EMF, then the induced current I will be, well, if you know E and I, we have the resistance of the coil. Therefore, induced current I will be EMF divided by the resistance R. Alright, in the first case, what is the induced EMF? The first case is the coil is moved to the right. If the coil is moved to the right, the magnetic flux is not really changing. There is not much change. The number of lines of force crossing the coil remains the same when it is moved to the left or right. So the induced EMF is d phi by dt, the rate of change of flux linked with the coil. When the coil is moved to the left or right, the area of the coil inside the magnetic field does not change. And as the area does not change, there is no change in the magnetic flux. And if there is no change in the magnetic flux, there is no induced EMF. So in the case when the coil is moved left or right, the induced EMF is 0. Since the rate of change of flux linked with the coil is 0, there is no induced EMF, and therefore there is no induced current in this case. How about when it is moved up into the magnetic field? That means the area that is inside the magnetic field is increasing. So when the coil is moved up, the length of the coil inside the field change. Now the total length is 30 centimeter. Let's assume that at any given time, let x be the length of the coil inside the magnetic field. Now this is actually x. Now as the coil is moved into the field, that x increases. And we are told that the speed with which the coil is moving is 2 meters per second. If the coil is moved up, it means the rate at which x is changing is 2 meters per second, or dx by dt is 2 meters per second. Well, the flux linked with the coil at any given time, remember the flux is the number of turns times the magnetic field times the area. Now, what is the area of this coil inside the magnetic field? The area will be width multiplied by the length. The length of the coil inside the field, we said, is x. Therefore, the area of this coil inside the magnetic field is 0.2 times x. And so the flux linked with that coil will be N times B times 0.2x. The induced EMF is the rate of change of flux when the coil is moved up and is given by E equal to d phi by dt, which is d by dt of NB times 0.2x. And N is a constant, B is a constant, and what changes is x. Is that right? And we know the rate of change of x. That will be 0.2 NB dx by dt. And we know dx by dt, that is given to us. And substitute all those. You have 0.2 times NB times dx by dt. That gives you the induced EMF is 25.6 volts. If the induced EMF is 25.6 volts, what is the induced current? Induced current is the EMF divided by the resistance, that is 0.853 ampere. Well, according to Lenz's law, the direction of the induced current is such that the magnetic field produced by it must oppose the cause of that induction. Is that right? So what is the direction? The cause of the induced current is an increasing field into the paper. Therefore, the magnetic field caused by the induced current must be directed out of the paper. Is that right? And therefore, if the induced current in this has to be out of the paper, coming out, look at that, coming out, then what must be the direction of the current? In order that the magnetic field due to the induced current may be out of the paper, using the right-hand rule, the current must be in the clockwise direction. In the clockwise direction, going up here so that the field is out this way, and going down so that the field is the magnetic field due to the induced current will be coming out on the left and on the right, so that it opposes the cause of the induction. And how about when the coil is moved down? When the coil is moved down, the amount of induced EMF will be the same, but it will be in the opposite direction. Okay. So this is the direction of the induced current when the coil is moved up, and when it is moved down, the direction of the induced current will be in the opposite direction. Let's now talk about eddy currents. What does eddy